So once again, I welcome you all to the reprisal of the quantum field theory lecture. This one is re-recorded because unfortunately in the first lecture we had the issue with the audio. It wasn't wasn't recorded, so we have to do it one more time for completion's sake, because the other lectures, the following two lectures, will be recorded as well. So okay, we sort out some technical issues. Okay. So this once again, most of you have probably heard at least part of the previous lecture, so I will try to once again go through everything, maybe a bit faster in the first half, but I will try to include all the I will try to make the information complete so that you can, in the worst case, if you didn't understand it in the first lecture, you can try to understand it now, and you can pause it and listen or re-listen to the argumentation and stuff like that. Okay, so let's get first to the reading material. There are some recommendations based on my experience. Obviously, once again, this is probably not the type of audience that would require or want to read some textbooks, which the list that I'm presenting really does consist of textbooks. So, but anyway, I am including them because I believe that they are integral part of the library of somebody, or at least like the digital library of somebody who's willing actively to or willing to learn in some active sense quantum field theory. So let's go by order. So the first one, the lecture notes, which are in Czech, these basically follow uh, quite in quite in detail. They follow the philosophy, let's say, and also the thoughts or the sequence of thoughts that are presented in this lecture. So the lecture notes that are highlighted in this first link, then they are most certainly complete. They most certainly include all the mathematical and technical information that is quite often glossed over in this lecture. So if you're interested in the details, or if you're just interested in having all the necessary information in one file, then this link will provide you these lecture notes, or these lecture notes will provide you that. These are the lecture notes for the first and second semester of quantum field theory, taught at the Institute of Particle Physics by Professor Jan Novotný. So the second is the quantum field theory and the standard model by Martin Schwarz, or Matthew Schwarz. And this textbook I quite enjoyed because it was in some sense modern, I would say. It had all the necessary information, or it was complete, but it wasn't unnecessarily overburdening like some of the others, for example. So it had very light, light touch, or light flow, or how to say. It was well read, it was well written. There are many analogies that in some other text might be considered heretical, but it just everybody does them. And this textbook is just really good material for somebody who wants to start from the beginning and learn quantum field theory. Then there is the Bibles by Steven Weinberg, the Quantum Field Theories, Volume 1 and Volume 2. Unfortunately, Mr. Nobel Prize winning physicist Mr. Steven Weinberg died on I think, on Saturday. So this is very unfortunate. So I would like to also dedicate this lecture in part to him, because he certainly believes it. By the way, Steven Weinberg is one of the physicists that united the electromagnetic and weak interaction, uh, which is now known as the electroweak theory, and that's basically what has gotten him the Nobel Prize. So definitely, these two volumes are certainly volumetric. They have the content, and yes, they are a good reference book, but they also the philosophy of the lecture notes and the philosophy of this particular lecture is most well tied with specifically the way how Mr. Weinberg approaches uh, the construction or the pedagogy or the thoughts behind quantum field theory. Because as we will see, there are many approaches on how to arrive at quantum field theory, but most people don't know that there are more than one, and it is interesting to know to see the construction from many different points of view, and this is exactly what Steven Weinberg presents, and most of all he shows and he makes strong arguments for why quantum field theory is necessary in the case of relativistic quantum mechanics. Then there's the introduction to quantum field theory, which is the usual textbook or course material for many quantum field theory courses in universities. It has all the necessary information, and it has certainly merits of its own. There are some calculations that are not in the other text, but also it lacks some information that are in the more either modern text by Matthew Schwartz or the more complete text by Steven Weinberg. So it's really these all of these textbooks somehow go well together. Then there is the QFT or quantum field theory in a nutshell by Antonesi, and this one is more like a night stool reading, something you want to keep by your bedside when you're going to sleep, because it has a very great many interest, a large number of interesting topics in quantum field theory and how it all relates to modern physics, basically. Not necessarily from the point of view of high energy particle physics, but he also discusses applications in condensed matter physics. He discusses gravity in his textbooks, the ties into the quantum field theory, and all of these things. So basically, it's a very chaotic text. It's not definitely not structurized like a textbook. It's not, I would say, not meant to be a textbook, but it is interesting in its own sense. Okay, so uh, this was the information concerning the reading material. So let's introduce the quantum. Well, what we're going to talk about. So maybe first let's talk about where quantum field theory shows up. Well, as you might know, that there is a standard model of particle physics, which is the most advanced physical models, which describes the elementary forces except or elementary particles and the forces of nature except for gravity. And this whole framework is described in the formalism of quantum field theory. So obviously, if we want to talk about the most basic building blocks of our universe, then we have to somehow introduce, at least in three quarters, talk in the language of quantum field theory. So that's one way. There are many mysteries in the quantum field theory or standard model. In fact, for example, the three generations of leptons and quarks, and there are, for example, so it is interesting to know, by the way, that there's pretty much there are not many reasons for why there are three generations of leptons or quarks, because before there was any theoretical prediction or any prediction about why there should be three generations of quarks, the muon was already discovered, and the tauon was soon discovered as well. So, however, the discovery of tauon somehow there was this was followed by some theoretical prediction that there should be also three generations of quarks, which wasn't known at the time. And this has something to do with CPT symmetry, which is something that is also described in the context of quantum field theory. So it is obviously the field on its own has many interesting topics, which are mostly related to elementary particle physics. And obviously, the context or the concept of quantum field theory is used in all of modern physics, or for example, in the study of the evolution of the universe, be it for the description of the cosmic microwave background evolving in time from the Big Bang to our current future, be it for example, in quantum gravity, where some approaches with spin 2 particles known as gravitons are also somehow being attempted. unsuccessfully, or description of the quark gluon plasma and whatnot. So obviously, in the history of the universe, at whatever epoch you look, at whatever research period you want to study, and in each one of them you will come into contact with quantum field theory. So obviously this is something that is interwoven with current or modern physics. So it is good to know the language of these modern physics. But it is not necessarily only in particle physics. Oh, this slide, for example, talks about theoretical or some theories uh, that are predicting that there should be also a unification of all the forces, as it was the case, for example, for weak or electroweak symmetry or theory, sorry. And there are some theories that predict that also this electroweak force should unite with the strong nuclear force systems and energy scales, and that should further unite uh, with the gravitation. So these theories are also described in the context of quantum field theories, are known as grand unifying theories, and or also in the context of string theory. And well, basically, yes, that's what I wanted to say. And it is not only the case of relativistic particle physics where the formalism of quantum field theory is used. It can be used, for example, to describe spin waves or magnons in condensed matter, uh, or ferromagnetics. It can be used to describe the lattice vibrations in crystals or in solid matter. They're known as phonons. These are the quasi-particles, or the there and then there is a great variety of quasi-particles that are used in condensed matter physics, like the polaron, polariton, I don't know, exciton, and many others that are also described in the context of this formalism of quantum field theory. And these theories are not necessarily relativistic, so the formalism itself is well employed throughout the whole uh, field of physics. So once again, it is language that is integral to modern physics, whatever modern theoretical physics uh, at whatever field of study. So it is indeed, I would say, useful to know about this formalism, but personally, I also find it somehow fun because it's like joy of learning, right? So the more you know about the way how we can describe the nature around us, the better. And yeah, so if we were talking specifically about some purpose of this lecture, then I would say it's for the fun, joy of learning. But obviously, as you can see, there are many, great many applications of quantum field theory or formalism. So we will talk about it. We will mostly talk about the relativistic variant, which is actually the harder one, and some of the non-relativistic theories. But we know that our universe somehow uh, uh, works under the laws of relativity, so we have to take that into consideration if you want to describe processes like, for example, ionization, pair production, or Compton scattering. So, and these are, for example, the processes that we are studying at Eli, well, in some sense every day, or it is inherent to the to the interaction of light and matter. So yes, basically, what this formalism also allows us to study is, let's say, electrodynamics in more precision. Specifically, this theory is known as quantum electrodynamics, which we will talk about mostly in the second lecture. In the first lecture, we will show the general formalism of quantum field theory. In the second lecture, we will apply this to quantum field theory, so or quantum electrodynamics. So this theory is the best theory to use for the description of electrodynamics. So that may be also uh, a good good motivation for somebody working with like optics and stuff to understand the nature of things that he works with in more detail, let's say. So first, let's talk about tests since we are, well, mostly concerned about QED. Then let's look at the tests of QED, or the brilliant results of QED, and which show, or for example, this process, the first process that we see right here. This is the The squibble on the left-hand side is something that's known as the Feynman diagram, which we will describe in later, or we will explain what this pretty picture actually means uh, in the later lecture. But this Feynman diagram is one of the Feynman diagrams that describes the process, or that are somehow related to the calculation of the process, where where electron and positron collides, they scatter somehow, and they deflect with some, let's say, different energy under some angle. This can be all calculated in the formalism or in the context of quantum field theory, specifically QED. And on the right-hand side, we see the differential cross-section, which is basically something like the probability that that one of the particles will deflect under some angle with some energy. So pretty much something like that, and its angular dependency, and the solid lines are calculated from QED for various energies of the colliding particles, total energies of the colliding particles, so the sum of the two energies of each of the particles. And we see the dependency, for example, on the angle of deflection, or the cosine of the angle of deflection. And we see a very nice match with the leading order contributions, analytical contributions to this process, calculated from QED to the experimental results, which are the various dots. So then there's, for example, another process that was studied, which is once again the collision of the electron and the positron, but now in the end state, or in the final state, we see that these two particles are somehow it's that they have annihilated, and they have and the outgoing particles are the is the muon and anti-muon. And once again, we can calculate this process in the context of QED, and we can, on the right hand side, you can see the cross section, the total cross section, which is the integrated, which is differential equation had some, differential cross section had some angular dependency. Total cross section is integrated differential cross section, so that's like, let's say, some total probability of some process depending on some total total energy, that this square root of s, is equal to the total energy of the colliding particle, so the sum of the energy of the positron and the energy of the electron. So this is the dependency, let's say, in some sense, of the probability, or the total probability of the process happening in some energy. To be specific, cross section has the area, or has the units of area, or let's say meters squared. So this can be somehow understood also as the effective effective area that some colliding particle needs to hit for a process to happen. For example, in Rutherford scattering, we have some gold foil, and we have the atoms being shot at some target, and the cross section can be understood, let's say, as the total area, some some target area, effective target area uh, that the incoming incoming particle, incoming alpha particle, has to hit, so it deflects. Let's say this can be, so this is like, but obviously there are different definitions. Like, for example, the number of deflected particles divided by the total power of the incoming, of the, that is, of the particles that are being shot on the target deflecting. So obviously it is in units of meters, but we can understand it heuristically as the total probability, because it is related to this probability very closely. Total probability of some process happening depending on some total energy. So this is the that was the total cross section for the process. This is the differential cross section for the process. Once again, we see a nice match with the QED. There is also some correction from the weak interaction, but anyway, it is the QED well describes these processes. But let's talk about what is known as the crowning success of QED, or the most brilliant result of physics, or the most precise result of physics. This is the comparison of the analytically predicted value of the anomalous magnetic moment, or the G factor, that is related to this magnetic moment, to the experimentally measured value. The magnetic moment is some sort of sense a response of the well, it is the or when we place a magnetic moment in some magnetic field, obviously it starts to wobble. In quantum field or in quantum mechanics, when we place a magnetic moment when in the magnetic field, homogeneous magnetic field, it gains some discrete energy levels, which are usually the difference, which is usually in the case of electron in microwaves. So you can see on the left lower right side of the slide that there is some contraption, some experimental way how to measure this anomalous magnetic moment, which is basically some microwave antenna that is shooting some microwave electromagnetic radiation, and it is inducing this dipole moment or this wobble of the magnetic moment loop, the electron that has some spin, right? So this is something like magnetic moment, and it is inducing these energy transitions. And obviously, this is some sort of a pump probe experiment where we can then measure the response of the electron and measure its magnetic moment. And it turns out, if we would calculate this just from the Dirac equation, this would give us a value G factor equal to 2. But in the end, from the measured value is slightly different. It is slightly more than 2. And if we calculate this from QED and also other parts of standard model, when we get to the precision of, as you can see, this is like the, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 at the 11th decimal number. So like this is crazy, crazy precision. And this is one of the most precise results. QED, so calculation of the anomalous magnetic moment of the electron. Oh, obviously, quantum field theory is used in many parts of physics. It's used in the energy frontiers, where there are many interesting topics like the origin of mass, the existence of dark matter, uh, matter, antimatter, symmetry, antisymmetry, asymmetry, stuff like that. And there's the intensity frontiers, where neutron physics are being done in the Kamiokande in Japan, for example, or where proton decay uh, is sort of well, people are trying to measure the proton decay, because if they would measure the proton decay, it would turn out that our standard model is incomplete, and there are some competing grand unified theories that predict this proton decay. So if we ever measure proton decaying, we know that standard model is not incomplete, and there are some candidates uh, for that for that could possibly predict this behavior. So, and then there is the cosmic frontier, measuring high energy cosmic radiation and the dark energy and stuff like that. So obviously, all of these areas are somehow using quantum field theory. So this was sort of motivation that shows that it is a language that is used all around the physics. So let's go through the lecture outline. So first some conventions, some notation. We'll quickly go through the convention of or what is. We'll do a quick review of special relativity. Then we will do review of classical field theory, which is usually at the bachelor level. Not the formalism. The general formalism itself is, well, maybe not always uh, explained in detail. Mm, the students don't practice it that well, so we'll quickly go through it. We will discuss something about Lorentz symmetry, what it means in the context of quantum mechanics, what it means in the context of classical mechanics, and we will review quantum mechanics. We will talk about the basic principles and how, for example, Lorentz symmetry is related to quantum mechanics, and how what is the result of the union of these symmetries and quantum mechanics, and then this will naturally lead us to relativistic quantum mechanics, and how we will want to construct this relativistic theory and what are the requirements. As we will show from this discussion, it will turn out that we need to consider many particle description, and we need a theory that has the notion of locality, which, as it turns out, is a concept that exists only in classical field theory, and the many particle necessity will lead us to the quantum mechanics description. And then as an example, we will illustrate the concept of field quantization on the easiest examples of all, the scalar field, which is a field that doesn't have any additional components. For example, the electric intensity, that's a vector field. It has three components, right? The Ex, Ey, Ez. Scalar field has only one. It's not a vector. It's a scalar. It's a number. It obviously depends on some position, so it has infinite number of values. But we will discuss this. We will, in the context of the review of classical field theory. So we will use natural units throughout the course, and which will be given as the reduced Planck constant is equal to the speed of light is equal to 1, and the units of observables are then some physical quantity are then given as the electron volt to the power of something that's known as the mass dimension of the quantity. What is the mass dimension? Well, let's look at some example. For example, the energy. Well, since C is equal to 1 and E is equal to mc squared, well then it's E is equal to m, so we can say that everything is measured in electron volts, right, in energy. So we can say that the mass dimension of energy is equal to 1. Okay, the same way for momentum, because momentum is again E equal to energy because C is equal to 1, right? So E is equal, for example, or E squared is equal to P squared plus M squared, so the units are the same. For massless particles, E is equal to P, so the units are the same. Then, for example, the time, well, the energy is, or for example, well, the units of time and the units of position are in minus the minus mass dimension. This is, for example, you can think about it, for example, from the point of view of the uncertainty principle, where you have the mass or the energy time uncertainty principle, which are inversely related. So if the units of the energy are in eV, then the units of the with Planck constant equal to 1, then the units of time are in eV to -1, so the mass dimension is -1. Then, for example, the mass dimension of the velocity is the mass dimension of length divided by time. So that's actually the difference of these two, and this example, for example, the same as the mass dimension of action is also equal to 0. More information about mass dimension can be, for example, found in the handy sheet that I gave you, or the lecture notes, that are in the that I provided in the reading material. But the important point is you can see it all relates to the units of energy. So all the physical quantities are given in powers of energy. That's all you need to understand. For the complete, uh, um, for the most important, for example, for the most important mass dimensions of some physical quantities, you can look at the handy sheet and see that, for example, the units are in such. The mass dimensions are, for example, such, and there are even some derivations. So anyway, this if you want to think about this in more detail, then just it really follows from the fact that we define the reduced Planck constant and the speed of light equal to 1, and then everything follows from that. So, and the fact that we consider the basic unit as the unit of energy, which is in eV. So everything follows from that. Everything is related to that. So, conventions and notation. Dobra. So, the conventions of special relativity, we have the position 4 vector. We have the contravariant version. We have the covariant version, which is simply uh, the one where the metric tensor lowers one index. This changes the space component, or the space part of the 4 vector. The space components are simply then, if we consider the Minkowski tensor, then the space components are then transformed to -1 in our convention, which is the usual particle physics convention in relativistic physics or relativistic mechanics, and like in such calculations, then usually like gravitational calculations and stuff, then usually the other possible choice is adopted, where we take the where we take the first component of the Minkowski tensor as -1 and the others as +1. Then, of course, then there are the space-time indices which go from 0 to 3. There are the time, the Euclidean indices which go from 1 to 3. So all the known stuff. There is the partial, or sorry, the four gradient, which is given from for partial derivative. We can also uh, um, raise its indices from by Minkowski tensor. This changes the gradient or the last three or the space components of the four gradient into minus. So this is also easy, and we can do the contraction of these two, which gives us the D'Alembertian, which is also sometimes called the Minkowski-Laplace operator, because just the uh, it is just the square of the four gradient. So this is just the special relativity that you should know. And before we get to quantum mechanics, let's talk a bit about classical mechanics and field theory, because this is usually something that is not very well described or discussed. Definitely there are, at least from my experience, I don't remember any exercises where we would actually calculate anything with classical field theory. So let's talk about it, and let's show how easy it is. So classical mechanics, we all know that this is simply described by some uh, configuration coordinates, and we have some n number, which is we have some n number of them, for example, and this is the number of degrees of freedom. For example, when you have a free particle, it can move along x, y, z. So we have three degrees of freedom. When we have a dumbbell, then the whole dumbbell can move along x, y, z. But it can also rotate along axis. It can rotate around the other axis, and it can rotate along also on its own axis. So these are 6 degrees of these are 6 degrees of freedom, for example. So this is all we know. The dynamics, for example, like the Newton's law or the Euler equations for a rigid body that give the dynamics for the for, for rotating rigid bodies and stuff. Then dynamics are simply given from the Lagrangian or the equivalent Hamiltonian description. So we have to construct some Lagrangian of our system. We have to calculate some Euler Lagrange equations that give us the equations of that are the equations of motions, or equivalently we have to have some Hamiltonian. We have to calculate some Hamilton's equations. So the usual business. In classical field theory, the only difference is now that we have infinite number or that actually we consider well, we talk about fields, and these fields we consider the coordinates, because, well, what is a field? That is simply the same as some configuration coordinate, except we have an infinite number of values of the field, because each field is evaluated at one of the infinite number of possible choices of the space. Let's call it space-time, or the position. So it obviously makes sense because at each point in space, for example, electric intensity, at each point in space, I can ask what is the value of the field. It will be one value, and there's infinite number of positions that I can ask this value. So we have infinite number of, in some sense, configuration coordinates, and these evolve in time similarly as, for example, the position of a particle does, because once again, for example, in classical field theory, to give you electrodynamical analogy, we have Maxwell equations. They evolve in time. Uh, the electromagnetic fields evolve in time under the action of Maxwell equations. So this is exactly the same. The difference between the field and the usual configuration coordinates is simply that we have infinite number of degrees of freedom. We can also consider some indices. That is the A, that also contribute to these degrees of freedom. A could be 1, A could be, for example, 3. In the case of a scalar field, the A is just the field has just one component. In the case of electric intensity, for example, the field has 3 components. So that's another degree of freedom in some sense. But in both cases, it is an infinite number of degree of freedom, because once again, we have infinite number of values at each point in space that evolve in time similarly as for example, the position of the free particle evolve according to Newton's law. So, and in further text or in further slides, we simply denote these fields as x and this x is meant to be according to our previous definition in the conventions and unit slide. The x is simply the 4 position, so this is just simpler, so we don't have to write the index everywhere. Because if we would use the actual like meaning of the index, we would contract it or something, then we would indicate it. We won't. But this is just simpler description. So the dynamics are described by action. In the classical mechanics, action is given by something that's known as the Lagrangian. It can be somehow related to a Hamiltonian, to a Legendre transform, and if it doesn't depend on time, then turns out the Hamiltonian is the total energy of the system. So this is something we know. The uh, dynamics follow from the principle of least action. In the classical mechanics, it is exactly the same. Once again, the fields are now the configuration coordinates. So we have to consider the Lagrangian to be dependent on the fields. But uh, in the classical mechanics action, or well, both theories are classical mechanics, just to so that you don't get some idea that these theories are separate. They are the same. We're simply describing different configuration coordinates. In the case of, for example, free particles, we are describing some configuration coordinates for a free particle. In the case of a dumbbell, we have some another configuration coordinates due to the rotation and stuff that we have to consider. No, now we're considering the fields themselves and their evolution. So these are our configuration coordinates. Just don't get the impression that these two theories are different. They are exactly the same. So the action is given by the Lagrangian, but obviously the fields depend on position. So we have to introduce the notion of Lagrangian density. So the total Lagrangian is actually the integral over all space, because Lagrangian is position independent. It only depends on the configuration coordinates, and uh, we have to integrate the Lagrangian density over all space. And when we plug this into the definition of action, then we get what's here on the right hand side. That's simply the action, that is the integral over the Lagrangian density integrated over time, as is usual. But also, since we're using the definition of Lagrangian density as it depends on position, uh, or our index of infinite number of degrees of freedom, it must be also integrated over this index, because it shouldn't depend, or this position, because it shouldn't depend on it. So that is simply the note or the treatment, or how we like describe classical field theory. If you want example, then for example, the Lagrangian density of the electromagnetic field in special relativity, that is usually in the special relativistic courses, that is usually shown. Then that is, for example, an example of Lagrangian density. If you calculate the Euler-Lagrange equations of this Lagrangian density, then you will get the Maxwell equations. That is, for example, and one example of the infinite many possibilities that we could consider for these Lagrangian densities. As we will see, there we can choose some principles on how to construct these Lagrangian densities. So obviously the equations arise from the principle of least action. If we consider the Lagrangian, for example, to depend only on the fields and therefore gradient, then we will get the usual form of the Euler-Lagrange equation. The Lagrangian density could be more complex. It could depend on the higher gradients of higher for gradients, like a second for gradient, or it could depend on the positions. But as we will see, there are good reasons why we should omit such Lagrangians. We will see that momentarily. And when such a field satisfies the equations of motion, it is said to be on mass shell. We will see later why. Uh, Hamiltonian description, obviously, as in classical mechanics, we need to define some canonical momentum. So in the context of usual classical mechanics, that's just the derivation of the Lagrangian with respect to the configuration velocity. It is exactly the same in the case of the field theory. We have to consider the canonical momentum is simply the partial derivative of the Lagrangian density with respect to the time derivative of the field, which is exactly the same as in the context of classical mechanics. This is the same thing. So we're deriving the Lagrangian density with the time derivative of our configuration coordinate, which is the same as in the actual derivation of this is slightly tricky, but obviously we don't have time to show this here, so just believe me or look it up. not that hard. And the Hamiltonian is then simply the Legendre transform. If we have the canonical momentum defined, then nothing stops us from defining the Hamiltonian with the Legendre transform, and that is once again the the that is the uh, sum over, or is the integral, since once again we are talking about everything in terms of the densities, not necessarily the. So once again, this could be also somehow considered like Hamiltonian density, what we see under in the brackets. So it is the product of the canonical momentum with the configuration velocity, and we subtract the Lagrangian density as is usual, and we get the Hamiltonian. So this is the definition of the Hamiltonian, and the most important part of classical field theory, that is, or in the context of classical field theory, is the Noether theorem. This is the most important. This is actually the reason why we're even talking about classical field theory, because, well, obviously, uh, we have some intuition about how fields work from, for example, classical electrodynamics, but there are most people, or at least like undergraduate students, or people who are studying experimental physics, or people who don't get exposed to these concepts. They don't have many experience with Noether theorem. So let's talk about that, because it is incredibly important, because it tells us that if we have an action that is invariant under some transformation, then we call this transformation a symmetry of our physical system. And if there is such symmetry, then there exists a conserved current that is given by the prescription that I'm showing in the big brackets, in the big bracket, or in the big box here, and this is known as the Noether current. So what does it mean that it is conserved? That means that if we do the four gradient of uh, this quantity, then it is zero. There are obviously many different or there are strange symbols, and we will explain them on an example in the next slides. So you will see how, when we indeed do have some symmetry, these this theorem really gives us conserved quantities. So so by the way, transformation in the context of field theory, usually we're transforming only for example, the positions, or the like four positions and stuff like that. Well, fields can transform as well. For example, as you may know, if we have, for example, electrical intensity, then if we transform it under parity or the inversion, then the or if we transform our mm, our coordinate system under parity, the inversion, then obviously the electric intensity is different as well, right? So we have to transform both the uh, coordinates, and we have to transform also the fields, and how the fields transform, uh, that is more involved debate, and can be you can arrive at the transformation properties in various ways. Most importantly, the Lorentz transformation properties, which are very important in the context of quantum theory. But usually transformations are also very simple. For example, once again, scalar. Well, scalar, if we do any kind of transformation, for example, coordinate transformation of parity, well, scalar doesn't change at all, because it's simply a number, right? So scalars, they're good because they don't transform. Uh, so let's do some. Let's before we do example, let's talk about, because I was saying something about the choice of a Lagrangian. Then let's specify what we mean by that. We will usually consider such action where the Lagrangian density satisfies the following conditions. So at most, we will consider first order derivatives. Why? Well, because if we would consider higher order derivatives, I don't know if you, for example, ever solved like or tried to solve or played with uh, Newton's equation, or Newton's law, Newton's second law, where you consider third derivative of position instead of a second one. But you will see that, for example, if you're considering like something like a step force input, for example, if you're considering something like a step input at some time, that there's some like delta force input, then your position, or your response of your system, you have like the Newton second law. Well, if we consider the third, or third time uh, derivative, then it might turn out that there are some issues with the notions of causality, because you might see that your system reacts even before there is some input. So this leads to natural uh, trouble with causality, because, and this is obviously a problem. We want everything that is causal, so that's one issue. There are also some what is it? There are some also some unstable solutions to such equations, and these are also problems. So this leads some to like infinite energies and stuff like that, or just unphysical accelerations and stuff like that, where you put some minor energy into a system and you get like infinite numbers of energy. So there are issues with this. So this is the reason why we're considering only first order derivatives. The second condition is Lorentz invariance. Obviously, we are mostly interested in quantum electrodynamics. Once again, quantum field theory could be uh, talked about in the concept of non-relativistic theories. Like, for example, we could try to describe the Cooper pairs, which are bosons in the superconducting theories and stuff like that. But uh, we will not do that, because we would rather uh, focus in these lectures on the quantum electrodynamics, because well, that is mostly related to our field. So we will discuss that. So our additional, but remember, this is optional. So our additional requirement will be we consider Lorentz invariant Lagrangian densities. We also want that our Lagrangian densities are local. What does it mean? It simply means that they're a function of one position. They can be a function of two, because, for example, if we had think about, for example, electric intensity. If we had like electric intensity that would be a function of two different positions, well, that means, for example, something like x time y, then this would mean that if we look at some space-time point x at the value of the electric intensity, so example x equals I don't know, for example 1, then this would mean that it depends on the second position, and this position could be any position, even ones that are space-like separate. So this would mean that our measurement of electric intensity is dependent on some position, and this is somehow a notion of non-locality. This is something that it is not the case that our measurement at some position should depend on some position that is space-like separated from us. So obviously we don't want that. So once again, think about Maxwell equations. You are only deriving, or like all your differentials are with respect to one choice of position vector, right? You're not solving with respect to many position vectors, because this leads to trouble, to issues with causality, because then you can get like faster than. So once again, locality is tightly or related to causality. So this is another requirement. So we want all the quantities that we are considering in our Lagrangian to be dependent on a single position vector or vector. And then we demand that our Lagrangian density is real. This is simply this can be understood from the fact that our action is real, because and obviously if you were integrating in time over some complex complex quantity, then it wouldn't make much sense. This can be there is even a better reason for why the action should be real, actually, in the context of path integral formulation of quantum mechanics, where it turns out that probability amplitude of some process happening is related to the complex exponential of the action. So if the action or the phase, so the phase is so the action is basically the phase of some exponential in these probability amplitudes, and these are complex values. But if the phase or if the action wasn't real, if it was complex, then what the hell is a complex action? That would be insane, right? So this is sort of like a heuristic argument for why it should be real. It is also another good reason is that it is related to a Hamiltonian, which which is somehow related to total energy, which is a measurable quantity. So Hamiltonian has to be the Hermitian, and so the Lagrangian should be Hermitian in the context of like matrix theory, which is quantum mechanics. We can take any Hermitian operator and transform it into a diagonal form where all the values on the diagonal are real. So this is like just some coordinate transformation. So the requirement of hermicity is in some sense is in the context of quantum mechanics is equal to the requirement of realness in classical field theory. So in classical field theory we want real Lagrangians, but in quantum mechanics it is good enough that they are Hermitian. Because once again we can always like the eigenvalues are always real, which are the measured values. And this is if you want if you're not if the path integral argument isn't good enough for you, then this is because it's related to Hamiltonian, so it has to be somehow real because Hamiltonian is somehow related to total energy or can be. And this form, so this restricts our Lagrangian density in the sense that it depends only on the field and it depends only on the four gradients, and it can also depend on the position. We will also omit that because if it was depending, for example, on time, well then our Hamiltonian wouldn't be conserved in time. So that's also problematic notion. So once again, these are there. Maybe I'm not too knowledgeable about theories where this position dependency specific the position dependency is considered in the Lagrangian, but obviously it leads to something like, for example, if you have time dependent Lagrangian or Hamiltonian, then your energy isn't conserved. If you have position dependent Lagrangian or Hamiltonian, then your momentum isn't conserved. So if you want these two conservation laws, then your Lagrangian or Hamiltonian shouldn't depend on position. So while these four requirements give us such form, then we can also forget about the dependency on the position. So this presented form of the Lagrangian will be the same as in quantum field theory. So now we're at the classical level, but already we are restricting our theories in classical quantum field theory. By the way, what does it mean to talk about theories? Theorists are talking about theories in the sense that when they're talking about some particular theory, they're only talking about some particular choice of a Lagrangian. So if I'm talking about the Lagrangian of quantum electrodynamics, then I'm talking about the theory of quantum electrodynamics. If I'm talking about the theory of quantum chromodynamics, then what I simply mean is that I'm talking about the Lagrangian of quantum chromodynamics. So don't be confused by this. This is theory. The respective theories are simply different Lagrangians. Easy. Okay, so now the example of Noether theorem. So it is the case, as we will see momentarily, that in the Lorentz group, which is the group that contains all the Lorentz transformations, there are transformations which are known as space-time translations, and we can consider the action of such a transformation on, for example, a scalar field. So scalar field once again doesn't transform at all. When we apply transformation to it. So in terms of the field, nothing changes. In terms of the coordinates, they are shifted by some constant for vector. They can be shifted in space. They can be shifted in time. So these are the space-time translations. And now we can calculate the infinitesimal field transformation that are talked about in the Noether theorem. This is the formula for the Noether theorem. This one down over here, and it shows us that we have to calculate the derivative of the Lagrangian with respect to the four-gradient of the field. We don't know the form of the Lagrangian. We didn't specify it, so we won't calculate that. But we also have to calculate the infinitesimal transformation of the field. We will calculate that. Then we have to subtract from it the four-gradient of the field and the infinitesimal transformation of the coordinates. And we have to add this Lagrangian and the infinitesimal transformation of the coordinates. To see how this form of the Noether current is derived, you can have a look in the classical field theory supplementary material that I sent you, and there you can see the whole derivation of the Noether theorem. So first, let's calculate the infinitesimal field transformation. So the infinitesimal field transformation is simply the first order term in the Taylor expansion of the difference of the transform field and the not transform field. That's simple as that. And since these difference of these fields, well, is zero because the transform field is exactly the same as the not transform field, then the infinitesimal transformation is equal to zero in all orders. So the first term goes to zero immediately, and what remains are only the terms with the infinitesimal coordinate transformations. So let's do the infinitesimal coordinate transformation. So we know that the transformed coordinate is simply the alt position vector plus the constant for vector, and we subtract the alt position for vector. Well, in all orders of expansion, this leaves us to just the constant vector. So we don't even have to do any Taylor expansions. So our infinitesimal translation is the shift vector itself. And for the purpose of convenience, as we will immediately see why we're doing that, we will also lower it, or we will write the shift vector with a lowered in the index, as it will as we will see immediately why. So if we plug this into the formula for the net recurrent, then once again the first term is zero. The second term we don't have to derive the well. This is we don't need to know the specific form of the field. This is simply such, so we leave it at that. Uh, we have the infinitesimal coordinate transformation, and then we add this term right here. We know that the infinitesimal coordinate transformation is simply this shift vector and the metric tensor, so we plug everything in, and we pull out the infinitesimal shift transformation. Now you can see why we did well, you don't see it yet, but okay, so this is our form of the net recurrent. So this is our form of the net recurrent, and if we assume that our action is invariant, once again, we didn't specify any Lagrangian, so we don't know if there is, but for sure, there are many actions that or actually most actions, that can be, if they don't depend on position, then they will be space shift invariant if they don't depend on the four position. So once again, this is our net current and the form that we've derived. And since this conserved current is also, well, this quantity is conserved for any value of the shift vector, then the following object inside the bracket is also conserved. This tensor structure that is known, it is known as the energy momentum tensor, and this is so basically this structure is also conserved. And this is we can calculate the conserved charges. So first, think about the four current as you've heard about it in the special relativity, for example. In the special relativity, the four current has the zeroth component as the charge density, and the space components as the current density. So it's some charge density, some current density, and if we want to calculate the conserved charge, so this is obviously a density value, then we have to do the integral over space of the density, right? This is some charge. So, and the density is the zeroth component of the for current. So in terms of our tensor, we know that our that is the zeroth component of the me, because we know that our for current is like its index is me, right? So we have to select the zeroth component of well, we basically have to set me equal to 0, and then since we have additional index, the index alpha, there are four conserved charges that are related to this energy momentum tensor. So first, we calculate the zeroth, the first the first choice, which is when we set alpha to 0. Then we simply plug it in, and we see if we did the calculation, we see that this is the time derivative of the field, so the partial derivative of Lagrangian with respect to the time derivative of the field. We multiply this by the time derivative of the field, the configuration velocity, and we subtract the Lagrangian density. So the 0, 0 component of the metric tensor is simply 1, and we know from our definition of Hamiltonian by the Legendre transform that this is equal to Hamiltonian. So the first conserved charge that we see is related to space-time translations is the conserved Hamiltonian, which is our energy in classical field theory. In theories that don't depend, or in Lagrangians that don't specifically or depend, uh, that don't depend on the position explicitly. That's the word I've been searching for. That explicitly don't depend on the space-time position. Okay, so we see that we have energy conservation due to time shift invariance. Then we have three more conserved charges. So we can choose all of those to the space components by selecting the alpha to be equal to I. Once again, the conserved charge is given by the integral over the charge density, which is the zeroth component of the net recurrent, which is as we said, the mu equal to 0. So we have these three additional charges, and if we plug there is a mistake here. There should be I. So sorry, no, this is correct. This is correct. As you can see from the definition of the energy momentum tensor, this is correct. This is correct. Okay, and if we plug this in, then we would, and if we knew the form of the momentum density in field theory, we would see that this is exactly the same form as the momentum density, or when it's integrated, this value in the bracket is momentum density of the field, and if we integrate it, then it's the total momentum of the field. Then we see that it is the total momentum of the field. Uh, so we see that we have momentum conservation due to translation invariance. So basically, we have calculated the usual thing that is claimed next to net recurrent, that when we have spacetime translation invariance of our theory, which we assumed, we didn't give any specific description of our action. We just said, okay, let's consider those actions that are spacetime invariant. That's no problem. There are many, and we see that we get the energy conservation because the conserved charge of the first component is the energy, and the additional three components are the individual momenta. So we have energy and momentum conservation due to space-time invariance. So this is already interesting. Then Lorentz, this is not the complete set of conserved charges of the Lorentz transformations. We have also Lorentz transformations like rotations, for example, and then we have also boosts. It turns out that the quantities uh, that are conserved corresponding to these two transformations, well, there's 6 in total. Uh, it is that these are the angular momentum. That is these are the conserved charges that are related to the rotations. And then there are what's known as boost generators. People don't have that much experience or intimate experience with these conserved charges, but they are related to the boosts, Lorentz boosts, in three different directions, right? For example, we can boost some frame along x-axis to some velocity. Well, there is a conserved charge that's called boost generator, Y generator. Maybe we'll discuss this. Maybe we won't. I don't really remember what follows. The discussion follows. Anyway, they are called boost generators because all these conserved charges, they are somehow related in quantum mechanics. They are related to the representations of the symmetries. So and they are given by some generator. So let's not discuss this now. But what is important that in Lorentz invariant theories, even at the classical level, there are four. As you can see, the momenta, boost generators, and the angular momenta have each three components. So there is a variety of, like, we can say, four conserved charges, and that is the energy or Hamiltonian, the momentum, and then there is the boost generators and the angular momentum. So these quantities are conserved in Lorentz symmetric theories. That's just interesting to know. And we could generalize in exactly the same manner as we calculated space-time translations. we could calculate these additional Lorentz transformations, which are the boost and the rotation, and the would lead to what's known as the Bellefonte tensor. We have gotten some energy momentum tensor. It had two indices. Well, the Bellefonte tensor, obviously harder translations, maybe more indices. So this Bellefonte tensor has three indices, and this is a tensor that can be used, for example, as the energy tensor or the energy momentum tensor in general relativity, because it is symmetric. It has all the properties of the energy momentum tensor that should stand on the right hand side of the Einstein's field equations and stuff. So this is somehow related also to, maybe in some sense, to special relativity and general relativity, where these tensors are considered for some calculations. Obviously, we know that special relativity works because, well, pedagogical example is that when we have solar energetic particles, which are for example, the protons that are emitted in the coronal mass ejections, hitting the Earth, then if they are very high energy, they can get to the atmosphere, and then they can decay, for example, to pions. These guys can decay to muons, and the muons usually are birthed somewhere around 15 kilometers. But there is an issue. If you calculate the decay lifetime, for example, from some theory, or if you could measure it in laboratory, then you would see that in the rest frame of reference, the muon has a decay lifetime of something like 2.2 microseconds. But if you are 15 kilometers above the ground, then for sure in 2.2 microseconds you can't get down to like the sea level where you can measure these events, or you can measure the tracks of the muon particles with like a bubble chamber or something. Well, but it turns out in the experiments we measure many more particle or muon tracks than we should, and this is specifically because there is something known as time dilation. So the decay lifetime, or the decay lifetime, is dilated from our frame of reference, so it is longer, and that's the reason why the particle can travel down to sea level and we can observe it. If we shift it to its frame of reference, then it will really be 2.2 microseconds, but depending on the energy, this can be dilated. So that's the reason why we see more uh, muon tracks down here on Earth than we should. If we just did this naive calculation that it should travel like speed of light time 2.2 microseconds, right? So something like hundreds of meters or something. That wouldn't really be 15 kilometers. So or like 50, 100 meters or something, 60, 100. Okay, so we know that. Right, we know that special relativity works. There are many, like there are GPS and stuff, right? so, so you know all of that. So let's talk something that you may not know. Well, and that is the general definition of Lorentz transformation. Well, it is the Lorentz transformations are defined such that they are the general linear transformations that preserve space-time interval. Well, what is the space-time interval? That is simply the square of the four position. So as you can see, there's the blue box over here, and the definition of any Lorentz transformation is such that if we transform it into some coordinates, then it is the square of it. The space-time interval is the same as the non-transform, or the old, as in the old coordinates, or we say that it is invariant, this quantity. But it turns out that any scalar product of any quantity with any quantity is invariant, and since we can also consider quantities that are not necessarily the position for positions, but also, for example, differences of four positions, and these also have to be invariant, then the most general linear transformation is inhomogeneous linear transformation. Where we do a linear transformation, this is just a matrix here. Oh, there is a mistake. There should be mu at this x, and we add some translation vector. So this is just, y equals ax plus b. This is just a linear transformation. So this is our definition. This is some vector. This is some matrix. This is some vector. So this is just some jumble of indices, but this is nothing that we are not comfortable with for years. This is a nice picture over here, where, for example, we can see how that from the point of view of the old coordinate system, how the new coordinate system looks. So if we have the old coordinate system, the space x and the time axis, then the red lines are the light cones, and if we do a transformation to some velocities that are larger than the speed of light, or sorry, smaller than the speed of light, then the new coordinate axis from the point of view of the old coordinate system looks such. It is somehow squeezed closer to the speed of light, and the invariant quantities are the squares of these segments, and in both coordinate systems they are the same. So that is pretty much it. This is somehow a pictorial uh, representation of the invariance of the space-time interval. So By the way, the group that is containing these transformations, under which we call some system Lorentz invariant, we say that then these such transformations are part of what is known as Poincare group, and this is the semi-direct product. Actually, this is not a direct product. There should be like a little vertical bar here, but since I didn't know how to write it, then this should be a semi-direct product of something that's known as the Lorentz group. That's the first guy over here, and something that's known as the Euclidean four-dimensional Euclidean group. The O13 notation simply stands for what's known as indefinite orthogonal group OPQ, which leaves invariant bilinears with signature PQ. What does it mean? Well, bilinears are simply our old and well-known spacetime intervals, and their signature, the signature of the bilinears, is simply the PQ. In our case, it is 1,3, since when we do the square, the the sign of the zeroth component is plus, and the sign of the other components is minus, right? So we say that the signature is 1,3, and such bilinears therefore correspond that are invariant. The other transformations that leave such bilinears with such signature invariant are simply belong to the indefinite orthogonal group O13. Indefinite because the signature is indefinite, in the sense that there is a different number of positive and negative signs. Okay, so this is it. Let's talk a bit about, well, this is just a simple illustration of a boost. We boost some coordinate that is going with some velocity, do frame shift, then we simply, this is once again, it is a linear transformation. So if we have some old coordinates and we apply some transformation metrics that can be derived from the definition of the Lorentz transformations, then we will get some new coordinates, and this is simply the boost. We didn't do any we didn't add any additional four vector translation. We're simply considering the boost. Once again, remember when we were talking about the set of all the Lorentz transformation, there were the boosts, there were the rotations. Rotations could be also linear operation. For example, it could be the rotation matrix applied to the position vector. Then there are the translations, right? And then there are the translations. Okay, so that's it. These are the boosts. The beta is the normalized velocity, and gamma, the relativistic Lorentz factor, is simply this guy. We know that. Okay. And we can use the definition of the Lorentz transformation to reveal something about the topological structure of this group. Well, this is somehow an abstract notion, but it turns out that it is very, very, very important when you start discussing the action of the Lorentz group on, or the transformation that are Lorentz transformations on our quantum mechanical quantities, like for example some quantum states and stuff. So this is very, very important to talk about the structure of the Lorentz group, because it has some non-trivial implications. So let's quickly just briefly go through it. So the definition of the Lorentz transformation can be rewritten I know that I have some mistake over here, so what we simply mean by this that we can write some scalar product of different of some four positions, uh, and if we transform this product, then it will be the same. What it simply means, if we write it, there shouldn't be any slashes here, and there should be slashes here. So and as but anyway, what this means what we would arrive at would be that the definition of, well, what's known as the definition of another equivalent definition of Lorentz transformation is simply that these are such Lorentz transformations, there are such Lorentz transformations that leave the Minkowski metric invariant. In matrix form, we could write it as such. It would be simply that if we have some matrix, it's the Minkowski tensor, the matrix form of this tensor, then if we acted with this tensor on the Lorentz transformation matrix, you saw the matrix on the previous slide, and then we acted on this product with the transpose of the matrix of the Lorentz transformation, it would be the same as the Minkowski matrix. So this is just an additional uh, an additional version of the Lorentz transformation definition that's basically equivalent to the demand that the bilinears are invariant. You can try to write this correctly and you will see that this is the case, or just look at the Wikipedia, it's there as well. And this is useful actually, because now let's consider some specific, or just block some choices of the indices into this definition. Well, for example, in the first case, we don't have to even plug anything. We just take the matrix form and we act on this matrix form of the Minkowski tensor with another Minkowski tensor from the right-hand side. So this means that on the left-hand side we get 1, right? Because Minkowski tensor, because it's well, diagonal matrix, and you multiply it with another diagonal matrix that has ones and minus ones on the diagonal, then you get plus ones. This is the unity matrix. So on the left, and we are considering the determinant of this equation. So, or the equation where the Minkowski matrix is multiplied by another Minkowski matrix. So on the left hand side, we simply have 1. We do the determinant of it. It is 1. On the right hand side, we have the determinant of this guy. Well, we use simply the definition of determinant, which is that we can separate the determinants, and the determinants of the Minkowski matrix are 0, minus 1. There are two of them, so it is plus 1. And what this leaves us with the determinant of the transposed and the determinant of the non-transposed. Well, and this is simply the square of the determinant of the Lorentz transformation. So this gives us that the determinant of the Lorentz transformation is equal of any Lorentz transform, or some Lorentz transformations, but it is equal to either plus or minus 1. Okay, that's that's for the moment doesn't seem that interesting, or like what could come out of this, right? Well, you will see momentarily. Then I can consider a specific case of the definition of Lorentz transformations. If we plug in the me and me equal to 0, then the first box becomes basically, if we plug it in, a 0 Minkowski tensor at 0, 0 is 1. So we simply, and there is some scalar product between the Minkowski matrix and the Lorentz transformation on the right hand side, right? So we have to rewrite this. There is the position components are with minus 1, so we put them on the right hand side next to this 1, because me equals Minkowski matrix 0, 0 is equal to 1. That's this guy. Oh, sorry. That's this guy. On the right hand side we get me, ni, and the scalar product of this guy with this guy. So we have or the contraction of these two tensors with this. So this is simply the 1. So the Minkowski matrix is the 1. We get 0, 0 component here. Then there is minus, or let me write it for Marek here. So unfortunately, you listeners can't see what I'm writing, but you can look it up somewhere. So anyway, so the equation becomes a alpha, a beta, 0, 0. Oh, sorry, yeah, like this, an alpha, beta. And now we simply contract. So this is a 0, 0, A0 minus A I 0 A I 0, and the Einstein summation, so over I. This can be simply written as a, oh sorry, 0 0 square minus a 0 I square. So this is the equation that we have gotten, because this is a diagonal, right? This is a diagonal matrix. So it has to be only such components. So in fact, this is the definition of a scalar product. We have vector here, this is a vector, and we have another vector here. So this is just the square of the vectors this is just, something like, and it is this 0 0, or like that, the square of the zero. So that's this equation. So what we obtain is this equation down here, and we see that it has the 0 0 component of the Lorentz transformation matrix, or the square of this 0 0 component of the Lorentz transformation has to be equal to 1 plus the I0 component square of the component. So therefore, since this is a square and it's not a complex quantity, then it must be greater than or equal to 0. So we get another like separating condition between the different various transformation, is that there are some transformation whose 0 0 component is larger or greater than 1, and there are some whose component is smaller than equal to -1. Okay, well, this in fact gives us 4 possible sets of Lorentz transformations. These are known as the 4 connected components of Lorentz group 013, but they are not simply connected. This means that in the topological sense, there is no continuous curve that is connecting between these components. And but what is important is that we saw, for example, that there are some transformations whose determinant is, for example, -1, and whose component is -0. Well, in fact, the 0 0 component is -0. For example, this includes the time inversion transformation. Or in the opposite case, there are some transformations whose determinant is -1 and 0 0 component is +1. Well, then this includes the parity transformations. And the last case, the components whose determinant is 1 and whose 0 0 component is -1, this includes the composed PT transformation. These transformations belong to 4 different sets of Lorentz transformation. First of which is known as the proper orthochronous Lorentz subgroup, also known as the restricted Lorentz group. That's a very long name. And the combination or the union of these two sets is also known as the orthochronous Lorentz subgroup. The other guys are the antichronous Lorentz sets, the components, because they do not consist the subgroups, since they do not contain the unity component element. So just some, but what is important that all of these general Lorentz transformation can be related to this RLG, the red set, or that is actually a proper subgroup because it contains the unity element and all the good stuff. And it is enough, therefore, to study this RLG component, because all the other components or all the other Lorentz transformation in all the other sets can be simply obtained by the action of these P, T, and PT matrices on the various Lorentz transformation in the RLG group. So therefore, it turns out that it is in quantum mechanics where we need some representations of these Lorentz transformations. It is enough that we simply consider the Lorentz transformations in this RLG, and this simplifies the things greatly, because then we can, for example, do like expansions around unity, which gives us nice representations of the Lorentz symmetries and stuff. So it is enough to consider this RLG. So this is just some side discussion about Lorentz symmetry. Also, since as we see that the Lorentz group is not simply the components of the Lorentz group are not simply connected, then there exists a theorem that says that there are no finite dimensional representations of the elements of the Lorentz group. Sorry. And this is incredibly important because this relates somehow to fields, and yeah, so this is very important. Okay, so before we get to quantum mechanics itself, let's quickly describe Lorentz symmetry in quantum mechanics. In quantum mechanics, symmetry is represented by unitary or anti-unitary operations, which are representations of elements of symmetry groups. What does it mean? Well, why unitary or anti-unitary? Well, from this defining relation on the right-hand side, you simply see that symmetries in quantum mechanics are such transformations which leave the probability intact. That is the definition of the transformation. And this immediately gives us the definition that the transformed states should be transformed by unitary transformations, because then the u plus u is equal to 1 and the transformed probabilities are the same. And the statement that the physical system is Lorentz symmetric is simply then equivalent to the following to the following relation, where basically if we do, well, Hamiltonian is something like a matrix, right? So we do like a matrix transformation with respect to the representations of the, for example, the Lorentz transformations, and it should be the same as the old Hamiltonian. So this is the statement in terms of the quantum mechanics when system is symmetric. So it is. So now the something that we can't do here, but we must mention here, is that it is possible to classify the irreducible representations of SO13. By the way, SO13 is the RLG, that's the restricted Lorentz group, because it has determinant equal to 1. And the S simply means it's known as the special indefinite orthogonal group, and the special groups are simply those that have the determinant equal to 1. This is somehow all described in the context of Lie groups, these called continuous, uh, these groups of continuous transformations. So it turns out that these is possible to classify the reducible representations. So once again, we said that the Lorentz transform or the representations of the Lorentz transformations have to be infinite dimensional. There's some theorem that says that, and they are reducible, so they can be reduced. Well, they can be transformed to block diagonal forms, and these block diagonal forms, it turns out, these are known as the irreducible representations, and these uh, representations act on their own, act on Hilbert spaces whose dimension is dictated by dimension of the irreducible representations, or the matrix, or the dimension of the matrices. So, for example, this is just a simplified example, but for example, or specifically the dimension of this Hilbert space is 2s plus 1, where s is some number that is discrete. These irreducible representations have some dimensions that goes with some discrete number, and that is it goes as 1 or it goes as half integer and integer. And we see that even before we actually start like quantizing anything, it turns out that representations of Lorentz transformations has something to do with spin, because they give some additional structure to the states in the Hilbert space. But what are actually, so basically we see basically that the Lorentz transformations themselves are somehow related to spin. So that's just some like side discussion concerning this. For example, the dimension of the Hilbert space, or the states in the Hilbert space for a scalar, would be 1. It doesn't have any additional components. If we were considering states which already have some spin dependence, then their dimension would be equal to 2. And this is related to uh, to irreducible representations with uh, that are 2 by 2 times 2 square matrices, and these are in fact the Pauli matrices, for example. So you may know that these Pauli matrices are somehow related to spin, and we can go on and on. The dimension of the Hilbert space. So as you know, the Pauli matrices, they're acting on states in the Hilbert space that are two component, but we will see all of that. In fact, we will arrive at these results independently when we start talking about relativistic. But in this context of the Lorentz symmetry, I just wanted to point out that the Lorentz transformations themselves, or specifically their representations, already encode the information about spin. And that is somehow deep, I would say, in some sense. So, quick revision of the quantum mechanics. We set the natural limits and the postulates are we are considering physical states that are described by some abstract rays or some vectors or rays in a Hilbert space, which is a linear vector space with scalar product, and the wave function is simply these abstract rays in the Hilbert space projected onto some defined position vector, position state vector. And in other way, we could interpret these wave functions to be the values or the coefficients of the uncountably many components of the expansion of the state vector in position representation. For example, you may see here, if we simply take some abstract ray in the Hilbert space and we plug in the completeness relation, where these states are the states with defined position, which means that if you act on them with position operator, you simply get the position eigenvalue. They are defined as such. And what we want to show by this is that the wave function is just the components in this sort of something like a Fourier transform, it looks. But more importantly, the Copenhagen interpretation tells us that the wave function represents probability density amplitude of finding our system in physical state that is corresponding to this ray in the Hilbert space, which means that the probability itself of finding some uh, 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 finding some physical state, for finding some system in some physical state is just the square of the wave function in, for example, the position representation. So usually, concerning time evolution, people postulate the Schrödinger equation. Well, I want to do something else. I want to postulate the conservation of probability. I want to say, or it some sort of feels natural, that the norm of the vector norm of these vectors in the Hilbert space shouldn't change in time. So this dictates that the time evolution must be unitary, because obviously the vector norm of these is connected to probability, right? And we would like our probability of some process, for example, or something else to not change in time. So this is seems somehow natural, and this dictates that the time evolution must be necessary. So if we do the square or the scalar product or like norm, this is the norm of some state in the Hilbert space, then if it is evaluated at some time, then that simply means that it is given or it has been evolved from some previous time t0 by some unitary operator, and so it is indeed conserved in time. It must mean that these operators are unitary, which means that they simply satisfy this condition that, well, they are unitary operators acting on some states. And we will see that the unitarity of time evolution has many important consequences either in quantum mechanics or QFT. But okay, so this is what we got. It is also somehow natural to demand that the time evolution can be composed. For example, we can first evolve our state from some time t0 to some time t1 with one application of the time evolution, and then we can evolve the state from some time t1 to some time t, and it sort of feels natural that this should be the same as just evolving the state directly from t0 to t. So this is another demand, and this tells us, and the combination of these two gives us it is sort of a theorem that every unitary operator satisfying these two conditions, well, it is unitary and can be composed, can be written in the following exponential form, where the h operator is some Hermitian operator. And now, if we consider the conservation of energy, then we can take this Hermitian operator as a Hamiltonian describing our system. Because if we do this if we evaluate the time, well, if we do the time derivative of the of this H operator in Heisenberg picture, which is simply the transformed Schrödinger picture, we'll see on the next slide the definition of the pictures. Then, if we derive all the three terms, and in Schrödinger picture no operators depend on time, so this is immediately zero. and the derivative of u from this equation, this first equation, simply gives us minus IH. The derivative of the complex conjugate gives us plus IH, or this is equal to the commutator of H, which is obviously 0, right? This is minus 1 plus 1 is 0. So this operator H doesn't depend on time, which means that it is time invariant quantity, and as we know from classical mechanics, this usually corresponds to energy. When there is some conserved quantity that relates to the time shift invariance, and it is usually energy. So we can say that our H is Hamiltonian, and this alternative approach we just done is simply equivalent to the postulation of Schrödinger equation, but it seems somehow more natural to demand these things than to just say that, hey, there is a Schrödinger equation. If we wanted to produce the Schrödinger equation, then we would simply act with the time derivative on this equation, and we would get immediately the Schrödinger equation. So this is equivalent to postulating the Schrödinger equation, and it can be also derived, for example, by looking for the operator form of the equation, non-relativistic equation, that the total energy of some, let's say, free particle, is equal to its kinetic energy and its potential energy, roughly speaking, where we would consider the kinetic energy in its non-relativistic version. But we see that this approach is sort of more natural, because not many people are satisfied with just some postulate of the Schrödinger equation. Okay. Probability amplitude is then simply the norm or some projection of some initial state onto some final state. And once again, if we evolve the initial state in time, or we take some initial, well, probability amplitude that some process happens is that we take some initial state at some time t0, we evolve it at some time t, and then we project it onto the final state at time t, and this is our probability amplitude of some process happening. We know what is the evolution operator, and we can act with the evolution operator on the ket vector, which basically evolves it back in time. So we see that even probability amplitudes are conserved in time. Also, quick review of the Schrödinger dynamical picture, just so we don't get confused in the notation. Well, we probably won't use them anymore, but it is good to review it anyway. So the expectation value of any operator, for example, this would be a probability amplitude if the operator was unity. It would be simply the uh, the scalar product or the vector product, well, the product of the scalar product of the final state and the initial state at some time t, which is the on the last slide we saw that this is the probability amplitude. Or if we consider some operator, then it is the expectation value of some, or transition. For example, I know we could consider something like a transition dipole moment that is some matrix element of the dipole. Or if, for example, we considered the operator to be unity and the initial to be equal to the final state, then this would be simply the probability of some particle being in some state, initial state, and stuff like that. So this is just some. So in Schrödinger picture, the operators don't depend on time, and only the state vectors are evolved according to the Schrödinger equation. In the Heisenberg picture, we simply take the evolution operators that define the evolution and simply redefine the operator into what's known as Heisenberg picture, where we simply take the evolution operators from the state vectors, and we say that, okay, that this is a new quantity that is depending on time, and we call this operator in Heisenberg picture. And this Hamiltonian is usually given in terms of a free part and interacting Hamiltonian, or free Hamiltonian and interacting Hamiltonian, because this separation has is important in the Dirac picture. So we see that in Heisenberg picture there's no time dependence for the state vectors, and in the Dirac picture all the components of the amplitude, probability amplitude, or matrix element are time dependent. And in this case, we simply take the rest or free Hamiltonian part of the Hamiltonian and define the operator to be such. So we simply keep the rest Hamiltonian part of the Hamiltonian, and uh, we also define the interacting or the state vectors with the free Hamiltonian part. So basically, what this does is that it leaves in the actual evolutions only the interacting parts of the Hamiltonian. And oh, by the way, I think there should be an I here in this direct definition of the operator. Never mind. What is important that in the Heisenberg picture, only operators are dynamical, and in the Dirac picture, they evolve only due to the interacting Hamiltonian. So basically, we, let's say, neglect the oscillator or the dynamics, the complex oscillations that are due to the there are no dynamics in the free part, and this is good because then you can somehow rewrite the time evolution only for the interaction Hamiltonian, do some, for example, perturbation theory and stuff like that. So Dirac picture is the only approach that is usual, or that is the approach that is used when you want to calculate for example, some time uh, dependent perturbative expansion of some probability amplitudes or something, which is exactly what we will do in the next lecture when we start talking about interactions and QED. So now let's talk about what's wrong with quantum mechanics. We will immediately see that the issue of the usual choice of the non-relativistic Hamiltonian for a free particle leads to some complications. If we calculate the probability and amplitude, which is simply the evolution of some state, we first take some defined state. If we consider a particle being in some defined state that is given by some position state vector, defined position state vector, we evolve it to some time t or to some time t and to some time position x flash. Then we calculate the whole probability amplitude. Then it turns out that we are left with a function that is non-zero when we consider space-like separated space-time intervals. This is obviously problematic because this means that our particle can evolve, for example, in space-time diagrams. This means that our particle at 0x can evolve to some space uh, to some space-time position tx slash that is outside of the light cone. Basically, what we mean by this is that the probability amplitude is non-zero when we are considering faster than the speed of light evolution of particles. So we see that if we choose non-relativistic Hamiltonian, it is sort of like intuitive. Okay, I mean it makes sense that if we consider non-relativistic like Hamiltonian, we probably won't get relativistic evolutions, right? Well, we see this explicitly here. So this means that causality is violated because we get a little faster than the speed of light travel. Not good. And there is non-zero probability that the particle can travel or faster than light, basically. So that's a problem. But these postulates, in some sense, that we've talked about in the previous slides, that define quantum mechanics, don't dictate anything about the time evolution except from the fact that the h, or like it's a unitary, and there is some Hermitian operator h, which we identify as the Hamiltonian, that should uh, that should be Hermitian. That's it. Like that's the only requirement. So we could choose Hamiltonian to be completely arbitrary. For example, we could try to improve it with a relativistic energy momentum relation, right? Because like the actual version of energy is E squared is equal to P squared plus M squared in natural units. So the E, or the energy, is the square root of the P squared plus M squared, right? So, for example, in the non-relativistic Hamiltonian of free particles, we are only considering like P squared over 2M or something, right? Which was here. Yeah. So why don't we take the relativistic version? Well, that leads to problem. First, the Hamiltonian is non-local. This can be shown somehow that when you have an infinite number of derivatives, and that there is a problem. But that's not the most important. Well, it is an issue, but because we were talking about the concept of locality and how it is somehow also related to causality. But even when we calculate the probability amplitude itself, we see that causality is once again violated because now we're getting at least exponential decay beyond the light cone for the evolution of a free particle, but it is still non-zero. It is exponentially declining when we are considering probability amplitudes beyond the light cone of a particle, so this is better in some sense, but it is still non-zero. So again, not good. So this can be somehow healed if we apply the Schrodinger equation twice. You know, so we have the Schrodinger equation, right? The time derivative of some wave function is equal to h, right? And the h was equal to this a relativistic energy momentum relation. So if we apply it twice, then we simply get that we get now a square of this square root. So we multiply the square roots together, and we use the definition of the momentum in representation in one dimension just to make it simpler, which is the momentum operator in X representation is simply the partial derivative with respect to X, for example. In 3 dimensions, it is the gradient. And if we put uh, put the put the right hand side to the left hand side, we move it over. Well, you add, subtract right hand side from both sides. Then we add together their derivatives. They give us the D'Alembertian. So, and there is this additional plus m squared term, and this is known as the Klein-Gordon equation. Remember, the D'Alembertian is simply the wave equation operator, right? So this is sort of like a wave equation where there's some additional mass term, and we obtained this simply by, okay, so the first step was that we considered the Hamiltonian to be relativistic, and it was non-local and stuff, but okay, we said let's try like just to apply the Schrodinger equation twice, like for the fun of it, and we got this Klein-Gordon equation. Okay, yeah, that seems like equation, all right. There is trouble with this equation as well, but not so much. Well, first of all, it is manifestly relativistic invariant. What does this mean? Well, the D'Alembertian is manifestly invariant because it is the square of the four gradients. So it is a scalar. If we do a construction, if we do the square of any four vector, then that is a scalar. So that is a scalar, and m square is a rest mass, doesn't transform. Or that's a scalar. That's not some. That's not some. That's just a number. That doesn't. It's not some part of a four vector or something. So it doesn't transform in any way when you do Lorentz transformation. It's a scalar. Both parts of the equations are both terms are scalars. So it is manifestly relativistic invariant, or it is also in the context of relativistic invariance of equations. It is sometimes also said that they are covariant, but this technical term has also other definitions, so I would stick to relativistic invariant. So this equation is manifestly relativistic invariant. However, it can be shown that the probability density, which is the square of the wave function, that it, oh, and if we consider the total probability or if we integrate this probability density over some space-time region or space region, then there are issues because it can be both larger than zero and lesser than zero. This is we don't have time to show this, but you can just look at the Wikipedia or like the lecture notes, and you will see that it is possible. It's quite easy to show this, that it could be larger and greater than zero. This is also related to the fact that we basically have with this equation the uh, the uh, well, this is related to the fact, but that for these equations, the energy solutions can have the well, since we are considering the square root of energy, which is the E squared is equal to P squared plus M squared, then if we did the square root of it, right, we would get plus or minus square root of P squared plus M squared. Well, this is somehow related to the fact that this equation has positive and negative energy solutions, or solutions to which energies with the positive square root correspond and the solutions to which the negative square root corresponds. So this is problematic, and this directly leads to the fact that you can have this probability lesser or greater than zero, which is so it's indefinite. So because this ruins the probabilistic interpretation of quantum mechanics, because what is probability that is smaller than zero, right? So that's a problem. But not all is lost. It turns out that this Klein-Gordon equation on its own has some usefulness, and it is in fact related to the evolution of the particles that are the scalar particles that are with spin equal to zero, which are, for example, the Higgs boson or the pions or basically bosons with spin equal to zero, and these will correspond to fields with scalar fields with only one component, and these fields will evolve according to the Klein-Gordon equation. So, in fact, it turns out that the equation is not lost on its own. And however, in the context of this relativistic approach, or the search of a relativistic equation for a wave function, this is problematic. We need to interpret the wave function as some probability density according to the tenets of quantum mechanics. So most of the issues are due to the fact that it is second order. That's what gives us the positive and negative energies, and yeah, and also this is related to the fact that, for example, when you have a second order equation in time, then you need to supply not only the uh, initial condition for the function itself, but also its derivative, right? Its time derivative. This is because it's a second order equation. Also, if you have a solution for a second order equation, well, then this means that it is constant, the solution is constant only when you do the second derivative, right? So when you calculate the conservation of probability, or you calculate the first, uh, just the one, you apply one time derivative with respect to the probability, then you will get that it is not constant, because obviously the first derivative of the time derivative of the wave function is not constant, right? Because it is constant only in the second derivative, because it is given by the equation something like dt s is equal to m squared s, or something like that. So it means that only the second derivative is constant in some sense. Anyway, this basically issues all around. So there's so this is somehow all related to the fact that it is second order. So the Rex approach was, okay, so second order is problem, let's do a first order. And let's do it like completely generally. We just know that there should be some constant term, there should be, I guess, some momentum. So let's consider such a Hamiltonian, which is given by some whatever. This is the momentum. We know that it has three components, and we can also consider some constant term. And like for the hell of it, let's consider these operators to be also some, like each component of this vector, of this alpha vector, to be some n times n matrix, and this beta vector to be also some n times n matrix, to do it generally. In that case, the wave function must be also must have n components, because like if an operator acts on a wave function, well then how would an n times n matrix act on like some scalar, right? It must be a n component wave function. So the plane wave ansatz gives us the following equation. If we simply plug in, some plane wave, let's look for the behavior of the equation in terms of the plane wave, where this u function is just some, momentum component of the plane wave, some coefficient is component dependent, and we get this equation. And if we do the square of this equation, or we apply the Schrodinger equation twice, then we simply see that we get the e squared on the left hand side and some square on the right hand side. But we know what the e squared must be. It must be equal to p squared plus m squared. So if we do the square of this right hand side of quantity, we get some mess over here. But we know that it must be equal to p squared plus m squared, right? So there are some conditions that are following from this equation. From this, well, we demand that the mass energy principle holds. So these n times n matrices must follow the following conditions. By the way, this can be simply rewritten with the help of a commutator. This first square, right? Because if you write because if you write the scalar product, well, that is simply the AI times PI, right? If you assume the Einstein summation, and if we write the square, then there is two of these, so AJ PJ. Well, and we write it like this: AI AJ PI PJ. Then this this is a symmetric tensor, symmetric quantity, right? Because it's like if I change the coordinates, like it's the same, and this one as well. So we can just simply write this. We can simply write this like AJ divided by or like 2, like because right if I add it and just change the coordinates on the other side, and it's the same. So we can write this scalar product as this, and therefore the conditions for the matrices are the following. This is something. The conditions in total are something that like these are known, or the matrices or the elements that satisfy these conditions are said to be elements of something what's known as Dirac algebra. And so the first condition, as we see, it must be that this anti-commutator is equal to 2 delta ij, because then we wouldn't get the square root of p, right? Because then when this is equal to 2, this must be equal to 2 delta ij. So we get delta ij, and we get here delta ij pi pj. So this is just the square root of the vector, so this must be it. So the first condition follows simply from the condition or the requirement that we get the square of the momentum. Then there is the anti-commutator that should be 0, because we don't see any such linear term in momentum on the right hand side. And lastly, this beta matrix, the square of the beta matrix should be 1, right? Because we just get the m squared on the right hand side. Okay, so these are the conditions. And in fact, it is very easy to show that these conditions lead to the following, let's say, consequences. And it is so easy to prove that we will do it here with Marek together. So if we take the second condition of the Dirac algebra, then we can easily prove this first consequence, since we just write the anti-commutator, right? This is 0. Well, we can put this guy on the right hand side. We apply beta matrix from the right hand side. This is 1, and we do the trace. We use the commutativity of the trace, which means that we can just put the beta on this right here, and this gives us the beta square, which is 1, and this gives us minus trace alpha I, which is minus something is equal to minus something. Well, which means this is 1. For the alpha matrix, we can once again take this, but if not multiply with the beta, but multiply with the alpha I, and do exactly the same thing. And this will give us also that the trace of alpha I is equal to 0. So we get that the trace of alpha I and the trace of beta is 0. Now, the second consequence, that these matrices should be even. Well, why is this the case? This is because first of all, their square is equal to 1, And uh, uh, let me remember, their square is equal to 1, and yes, since their trace is 0, then this must mean that if we transform these matrices into some diagonal form, then their eigenvalues would have to be either plus or minus 1, right? Because their square is equal to 0, to 1, sorry. Their square is equal to 1. And since their trace is equal to 0, then when we sum up all these eigenvalues, they must equal to zeros. That means there must be an even number of pairs of plus ones and minus ones. Therefore, their dimension must be even. So that's the second consequence. And the third consequence stems from the fact that, in fact, so now there are the following possibilities, right? The dimensions could be 2, could be 4, it could be 2 by 2 matrices, it could be 4 by 4 matrices, it could be 6 by 6 matrices, they could be even, right? But let's look at the first case, the 2 by 2. Well, there is an issue with that because we have 4 matrices. We have the alpha, I, each of them there are 3, right? I is equal to 1, 2, 3, right? So those are 3 matrices. And then we have the beta. So 4 independent matrices, but unfortunately in 2 dimensions, or in 4 matrices 2 by 2, there are only the only set of Hermitian complex orthogonal matrices are the Pauli matrices, of which there are only 3. So this is the sort of a non-trivial proof, but because we would have to know that the properties of the Pauli matrix or the complex matrices in 2 by 2, but it turns out that there is only 3 such matrices that could satisfy the conditions. Obviously, they must be Hermitian because our Hamiltonian is Hermitian, right? So that is the case. Why I'm talking about Hermitian matrices all of a sudden. And since there are only 3 Pauli matrices, then and we have 4 matrices, we're talking about 4, then it must be the case that it is at least of dimension greater than or equal to 4, right? Okay. So yeah, that's the business. So this we proved, and this has deep consequences because if we do the most economic choice, the n equal to 4, which is, well, this is just what we've written, our assumption. Right now we know that these matrices, or like the elements of this algebra, like the representation of these elements, which are some matrices, they satisfy these conditions, which lead to these properties, and we can simply rewrite this into this equation into a manifestly covariant form, where we just define new matrices. This gamma 0 is simply the beta. Once again, these are not specified in some representation. This is just, for the moment, they are just some elements of this algebra. And then the conditions, these 3 conditions, are simply quantified in this only simple one defining relation. This is known as the Clifford algebra. These elements are part of what's known as a Clifford algebra. It satisfies this relation, and this is the usual form that these Dirac matrices are written. And so we know that from these relations, we got already some deep consequences. The matrices are in the most economic choice 4 by 4. Therefore, the wave function components are 4. And we've written the Dirac equation into manifestly covariant form. Yes, it is a bit more trickier to show that it is even that it is truly that it is truly Lorentz invariant, because now the wave function doesn't have just one component. It isn't scalar. It has now 4 components. It's not a 4 vector, but it's something else. It's known as Dirac spinor. We will talk about that later. And it transforms under Lorentz transformations in some specific sense, and that has to be considered. So it is not good enough to just say that this is a scalar and this is also scalar, because we have to transform accordingly also the wave function with respect to the Lorentz transformations. But even then, it turns out that this Dirac equation is indeed relativistically invariant. The form of this equation stays the same in all the coordinate or in all the frames of reference, which is what is meant by a manifestly covariant form. So Okay, so this is the covariant form of the Dirac equation. So we now know that it predicts four component wave functions, and if we did the low relativistic limit, we would get the Pauli equation, which is an equation for two component wave function. And for example, if we were considering also electromagnetic interactions, we would get that we would get we would understand or we would see how it relates to the notion of that these two components how they relate to the notion of a spin. There's no time to do that. Just Google Pauli equation or look in the lecture notes or in the textbooks. But or I can provide additional material where the Pauli equation is described. But if you ever saw usually in some quantum mechanics courses, the Pauli equation describes an electron that has also spin degrees of freedom. So this for Pauli equations, this electron has two components, like one, let's say, spin up and spin down, right? So it has now two component wave function. However, in the full generality of Dirac's equation, if we don't do any limit, there are additional two components. What are these? Well, we know that the eigenvalues we still have the same eigenvalues as in the Klein-Gordon equation. We have four of them. We have 4 by 4 matrices, right? So there are four eigenvalues, and there is an even number of them as well. And they are the positive or negative energies because they must correspond to these eigenvalues because the solutions of the Dirac equations are also solutions of the Klein-Gordon equation. This is simply proved if you apply the complex conjugate Dirac operator on the Dirac equation, then you will get the Klein-Gordon equation. So these solutions also satisfy Klein-Gordon equation, and we know that the matrices have the eigenmomentum equal to, or the trace is equal to 0. So the sum of these must be once again, the eigenvalues must be once again 0, and therefore the eigenvalues, the energies are once again canceling each other in parts. So it is somehow sort of related to this issue with Klein-Gordon equations. But now we have four components, so we need to dig a bit deeper about what the meaning of this. There may be some way to solve this, but now what's important is that the probability density is positive definite as since it is a first order equation, the norm is also conserved. So the probabilistic interpretation of quantum mechanics is safe. So such a relativistic equation for a wave function works if we interpret the wave function in the usual sense. Dirac suggested the following solution for the what are the two components of the wave function. And he claimed that let's imagine like energy states that are filled completely by a part what he claimed to be a Dirac sea, which is basically a sea of electrons, or in the energy diagrams. And since we know that there is something known as Pauli exclusion principle, this means that he claimed that this Dirac sea leaves only the positive energy states available. Quite some ad hoc solution that was devised in rush to somehow make sense of this, so that he doesn't lose face with these four components wave functions. And that when we excite a particle from the sea, it would leave a hole which would correspond. Well, basically, we would take some charge, some momentum, and some spin out of this sea. So this hole would act like a particle with positive energy, charge, and spin, right? Opposite spin. So the experimentalists actually were measuring antimatter for years, and it was usually discarded as protons. And the positron was in fact very quickly discovered when the discussion about these positive electrons started. And therefore the proper interpretation of the negative energy solution is the following. A negative energy solution, those we know that there are like two positive and two negative, right? Is either a negative energy particle propagating backwards in time, or equivalently, if you want to specifically understand this concept or the equivalence of the negative energy solutions and the positive energy solutions, then simply look at the homework assignment in the first page. There is a expanded discussion on the solutions of the Dirac equation, which I believe will make more sense. Anyway, or it is so it is a negative energy particle that propagates backwards in time, or equivalently, positive energy antiparticle, a hole in the Dirac sea with positive energy, which has opposite charge and spin, and it therefore propagates forwards in time. If we interpret it as some sort of like a antiparticle, so there's like a so this is how this interpretation was safe. So basically, these negative energy solutions were claimed to be positive energy particles that are acting as these holes in the Dirac sea, which have like positive charge. The electrons have negative elementary charge. These positrons would have positive charge, and the opposite spin of the excited particle. So still spin half half, but opposite with respect to the excitation. So, and this is just the diagram. Like if we have the negative energy, then we can simply rewrite it as a positive energy and get one spare minus, and this looks like a positive energy plane wave or plane wave traveling in the. Anyway, you can look at the homework assignment to make more sense of this. So this is just a picture of Mr. Anderson, the discoverer of the positron, sitting next to his magnet surrounded bubble chamber, and on the right there is the positron track, and it's curving due to magnetic field. The positron slows down as it travels in the lead plate. As you can see now, it has like a large radius of curvature with 63 MeV in the magnetic field, and after the lead plate, it has only 23 MeV, and it's like the curvature is much larger. This is because in the lead, it suffers inelastic collisions with lead atoms, and we see from the track curvature that it is a positive particle. It cannot be a proton because the proton would have stopped in the lead. But these tracks were in fact measured even before the theoretical prediction, but it was usually like claimed to be or somehow discarded as protons. So that's the reason why the positron was very fast, discovered very fast afterwards. And these Dirac equation solutions are incredibly important because they are part, or like this concept of four component wave functions or like the how to work with them, because they are part in fact of any QED or any calculation that involves fermions like electrons or positrons, for example, in the context of QED. Then somehow these Dirac equation solutions spring up. So it is useful to get a bit intimate with them, and this is actually the purpose behind the first assignment, which teaches you how to work with these uh, Dirac equations. So now let's have a quick break, and then we will analyze the implications of the Dirac equations after. So we're back from the break, and we're ready to discuss the implications of the Dirac equation. So we saw that the Dirac equation gave rise to the following things. Sorry, setting up the. Okay. So gave rise to the following things: the concept of an antiparticle, which, if we adopt the notion of Dirac sea, this can be interpreted as the uh, a hole in the Dirac sea. Let's say, well, this in fact corresponds. This is an equivalent description to the negative energy solution. So it is really a matter of choice. But in fact, these negative energy solutions indeed do act as the positive charged electrons. So equivalent once again. So we can consider this to be the concept of antiparticle. It also gave concept to many particle system because we saw that we had one particle, one antiparticle, and for each two spin components. So once again, we're increasing the number of degrees of freedom. And even when we're just talking about the necessity of relativity and the concept of Dirac sea, which on its own is somehow already an infinite number degree of freedom concept, because like we're claiming that in this system we have infinite number of electrons that are saturating the negative energy negative energy states. So on its own, like as a concept, it is for sure many particle infinite number degree of freedom kind of thing. And we start to see that the many particle description is natural even when we only require relativistic postulates or relativistic considerations for the quantum mechanics, right? It seems like we didn't require anything else other than the energy mass equivalence. And once again, in experiments, for example, we see the annihilation and creation of particles. So that is also must be somehow tied into this. If a particle has a kinetic energy that is, for example, 2 times some mass of some other particles, then it could, for example, create two particles with such mass. So we see that in experiment it is well known. So this description is unavoidable description of many particle quantum mechanics. It is intimately tied to relativity. And these points imply that we need the description that covers infinite number of degrees of freedom, or infinite particles, which can be sort of understood as infinite number of degrees of freedom. So, localization of observables. This is a concept that we postulated first for our Lagrangian density in the scope of classical field theory, right? In and it is only concept that, or in the sense, in the language of quantum mechanics, we can simply say that two observables uh, are well localized if they commute uh, for and they are evaluated in space-like separated areas or areas, then they must commute. This means that they are simultaneously they are simultaneously measurable, and the measurement of one of these observables does not affect the other. This means that they commute in the language of the quantum mechanics. So this is a condition that we will have to evaluate or check for all our physical observables. Uh, and we will have to construct our field theory or relativistic quantum mechanics in such a way that this condition is satisfied by the observables. And well, once again, as I was mentioning just before, localization of observables has no analogy in non-relativistic quantum mechanics. However, or in fact, relativistic classical mechanics, it has only analogy in classical field theory. As if you remember on the slide where we were talking about the action, the requirements for the Lagrangian, we were discussing the locality and how it relates to electric intensity. For example, or we gave the analogy or the example of electric intensity, and how such a concept is natural in classical field theory. There is no locality in this specific meaning or sense. For example, in classical mechanics, when we write the Lagrangian for a free-moving particle, there is no uh, concept for locality encoded into the math, let's say. So this sort of implies that a consistent relativistic quantum field theory or quantum theory, sorry, should be a theory of many particles and a theory with local observables. This is, of course, related to causality. And as we know, since the field theories are, there isn't the notion of locality, and there is the notion of infinite number of degrees of freedom, then they seem to be natural for the construction of relativistic quantum theory. So all these points, the whole discussion that was that we had just before, seems to lead us to some sort of quantization of field theory. And there is also a stronger statement, but we will go through that very quickly. This is known as the Weinberg conjecture. Once again, Mr. Steven Weinberg passed this Saturday, so as an honor to him, I will actually explain this conjecture. So suppose that we are trying to describe some relativistic quantum physics in some energy scale that is smaller than some cutoff scale. Let's say, I don't know, like electron volts to do 10 to the 300 electron volts or something. Some scale that is simply uh, very large, and we're trying to describe some physical theory below this scale. Then there an S matrix, which is simply the evolution operator in the Dirac picture, that is satisfying the following condition: that it is relativistic invariant, it is causal, it has what is known as cluster decomposition property, it is unitary, it may have some additional symmetry. For example, there is for each of the theories, quantum field theory, like quantum electrodynamics, quantum thermodynamics, or the electroweak theory, there are symmetries, additional symmetries associated with these theories. There is for each of these theories there is a symmetry, there is additional symmetry that is associated with the Lagrangian. This is different than the Lorentz symmetry, and this symmetry gives rise to the interaction between the particles. This is something that we will hopefully discuss either in the second or the third lecture. Then there is a conjecture that the most general S matrix, which is the central quantity that is described in any calculations, that is satisfying the previous assumption, can be constructed in QFT, and any physical theory must reduce to such QFT on this effective scale. So this is a conjecture, but it is it has there is no proof for this, but it seems to be the case as of now that any all the theories we have are described in these quantum field theories. So even though they may be effective theories, and there may exist some different theory or like more general theory on these scales, energy scales, where these quantum field theories work, then this general theory must reduce to these quantum field theories. So in this specific meaning, it is it is yeah we see that this is like another point why we should consider these quantum field theories. They seem to be this very strong formalism that we can use to describe relativistic quantum mechanics. To construct relativistic quantum theory, we need therefore the following key ingredients. In quantum mechanics, we know when we move from classical mechanics to quantum mechanics, we need some states in the Hilbert space, right? We need some. This is the postulate that we have something that's a Hilbert space and some states, some vectors that are part of it. So we need to identify what is this Hilbert space, and we need to interpret the states that are in this Hilbert space. As we will see, this will correspond to the one particle and many particle states. And the second condition, if we would be talking about only non-relativistic quantum field theory, then this would be only a requirement we would have, and the additional requirements would follow from, let's say, additional symmetries or some other requirements. But since we are specifically describing relativistic quantum theories, then we also need to find representations of Lorentz symmetries that are acting on the states in the Hilbert space. And we need to find the basis of local and causal operators that are acting on this Hilbert space. As such operators, they will form the basis of the physical observables. So there must be such a base, or there must be a basis of these operators that are local and causal, because they will construct, or they will they will work as the basis for all the physical observables. And if they will be causal, then that is okay. And then we can say that we truly have the relativistic quantum theory. So these ingredients, they are key for the construction of relativistic quantum theory, and each of them has to be checked, let's say, when we are constructing a quantum field theory. And to illustrate such arrival at quantum field theory, we will attempt to exemplify these three on the most simple case. But first, let's check the approaches that there are for arrival at this quantization of field theory. There are two possible approaches that produce these key ingredients. There is the first one, this is known as bottom-up construction of quantum field theory. This one is in some sense physical and intuitive, because we define the one particle states. We literally define the Hilbert space as, and we construct it from the definition of one particle states. This one particle states are defined as the eigenstates of formal momentum. This seems reasonable because we know that every particle is somehow associated with its rest mass, and in the rest frame, the form momentum, or the square of the form momentum, is simply the rest mass of the particle, right? Or, oh, sorry, in any frame, the square of the form momentum is the rest mass, because the square of the form momentum is e squared minus p squared, right? That is this one, and that is equal to rest mass. So in any frame, so it seems natural to try to define these one particle states as the eigenstates of the form momentum. And in fact, this leads to the observation that the Hilbert space is constructed as the Fock space out of these one particle states. Then the the local and causal operators that form as the basis of our physical observables are then some superposition of creation and annihilation operators on this Fock space. Because as we know, on the Fock space, the creation and annihilation operators are the only ones that change the states within, or that somehow interact on this state, right? Because, for example, if you remember from the quantization of the linear harmonic oscillator, if we apply the creation operator on the vacuum state, we get the linear harmonic oscillator excited to the, let's say that this is the vacuum, so these are the energy states in the harmonic potential of the harmonic oscillator, right? So we can with these with these creation and annihilation operators, we are somehow acting on the space. So these are the only operators, in fact, that can affect affect the state. And many particle states are then simply constructed out of the, well, yes, okay. And then there's the top-bottom way. That is non-intuitive, but very powerful. And it is so easy. You just take the classical fields and you quantize them. We will show, and once again, we will see that this immediately leads to the fact the Hilbert space must be a Fock space. So this is the quantization procedure. Well, then, of course, we have to check that there are the other two ingredients which are related to the Lorentz relativistic symmetry of our theory. The fact that there is, we know some transformation property of our fields, and that we have the local and causal operators. Then this has to be checked additionally. But the quantization can be done in two ways. Of the or the arrival at the quantum field theory, not necessarily relativistic, is done therefore can be done in two approaches, either like from this construction of the Hilbert space or just from the quantization of the classical field. We don't have the time to do the first one, but there is a text that describes it in the homework, but we will do the top bottom one, which is known as canonical quantization. So first we'll illustrate this procedure on the simplest case, the case of a real scalar field. So once again, we know that the most general Lagrangian density for scalar field, which you know from the classical field theory, right? We were discussing that the Lagrangian density must depend only on the field and on the four gradients. We want the conservation of energy and momentum, so we neglect the dependency of the position itself. And it can be shown that there could be some additional constants, but it can be shown that they can be transformed away, or sorry, that we can renormalize the fields, literally like dividing them by some constant values or stuff like that. And in the end, there will be only one constant that describes on which the or two constants on which the Lagrangian depends. This will be the constant term. Then there is some what's known as a kinetic term. This one obviously it has to be this form because if we're considering only the four gradients of the field and the Lagrangian density must be scalar, then we must contract it, and there is no other construction block other than the four gradient of the field, or there is no other vector quantity that we can consider other than the four gradient of a field to contract it with, right? So we have to contract it with itself. That's the one option. Obviously, there is a constant, that's a scalar, that's also good. And then we can consider the powers of the fields. The second power is a scalar, the third power is a scalar, just the powers of the fields. Because it's a scalar field, right? So we just can consider any powers of the field. And then there is some constant here. And these higher powers, however, we can omit, and this is known as harmonic approximation. We can omit this because these higher powers, they lead to nonlinearities. Well, this is our choice that we omit them, but these nonlinearities, they lead to the self-interaction of the fields, and this leads to nonlinearity of the field, which itself can be explored, for example, through perturbation theory, as we will do in the next lecture, and I hope we will get to the exploration of the self-interaction of particles and stuff like that. But what's important is that we want linear fields because, for example, think about electromagnetic field, right? When we have linear electromagnetic waves traveling in the vacuum, then we consider the principle of linear superposition to be okay, unless there are some like immense intensities in the field. There is some really like crazy energy at some space-time point, at which point this linear description stops working, and we indeed do see some like nonlinear electrodynamics and stuff. When you just consider like light in the vacuum, if it's intense enough, there might be some nonlinear effects. This is specifically this is what is this is, and it is in fact described in the context of quantum electrodynamics. Then it makes sense to first consider a linear approximation because we don't want to necessarily deal with the nonlinear nonlinear fields for the moment because they can't be even quantized nonlinear fields. So these additional higher order terms can be considered in as interaction terms, for example. And so this description is somehow valid near the or like in the case when you don't have too much energy uh, in one point of space-time, for example. As you can see, the Lagrangian density is space-time dependent. So at each point of space-time, there is some Lagrangian density. It has some values, and in the case when we don't have too much energy, too much in the analogy of light, too much intensity, then we can consider this harmonic approximation, and we can consider these fields not to interact, self-interact, which is equivalent to the linearity of the equations of motions. If we do calculate the Euler-Lagrange equations, then the equations of motion simply become the Klein-Gordon equation for this scalar field. For the moment, we're talking only in the context of classical field theory. We're not saying that this is some wave functions or anything. No, no, no. We're just talking about classical field theory. We consider the most, the given our assumptions about the Lagrangian density and that the fact that we want to the we want to talk about linear fields, and we omit these in uh, higher order terms, and we arrive at the Klein-Gordon equations. The Hamiltonian, we could do the Legendre transform to the Hamiltonian description, and it turns out that if we like wrote this integral in a discrete form, that this sort of looks like the Hamiltonian of infinite number of non-interacting harmonic oscillators, right? So this is exactly what we know from the description of the linear harmonic oscillators in quantum mechanics, that we can rewrite the Hamiltonian, and it looks like, in the case of many harmonic oscillators, as I said, sum of many harmonic oscillators. So this harmonic approximation gets its name from the fact that indeed you are sort of describing infinite numbers of non-interacting harmonic oscillators. So, and now comes the process of actual quantization. We promote the dynamical variables to operators acting on some Hilbert space, and we apply the quantization procedure. What is the quantization procedure? Well, in classical mechanics, there are some Poisson brackets, right, that are satisfied. For example, the Poisson brackets of the canonical configuration coordinate and the canonical momentum. They are, for example, they are equal to, like, for example, the Kronecker delta function. And the canonical quantization procedure is simply taking this and supplying or promoting these operators or promoting these quantities to operators and changing the Poisson brackets for their quantum version, the commutators. But plus, we must be also careful, depending on the type of quantity. For example, in our case, we will be quantizing fields. So depending on the type of quantity or on the type of field, we must either provide the commutation relation or the anti-commutation relation. Which to choose depends on the transformation property of the field, and as we know, these even from the Lorentz group, there was this correlation between the transformations or the irreducible representations of the transformations and the spin. So this knowledge of the Lorentz group also gives us the knowledge about transformation, and it, for example, tells us that the scalar field is the spin zero particle. It transforms as a spin zero particle, so it's boson. So we have to supply the commutator relators. For example, we could consider like spinor field, which would turn out to correspond to fermions. So we would have to supply the anti-commutator. This is related to Pauli theorem. It can be proved. It's very hard to prove it. We won't do it, but this is the usual quantization. And this quantization itself is related to Heisenberg uncertainty principle, right? Because if you write the Heisenberg uncertainty principle, for example, for the x, for the configuration coordinate and the canonical momentum, then it is from definition given by, or the inequality is given by the anti-commutator of these two commutator of these two operators, and so this is somehow tied. This quantization procedure, this promotion, is somehow tied to uh, quantum mechanics. Of course, you also have to, if you are promoting the quantities to some operators, you have to also make the assumption that there exists some Hilbert space on which they act. Right? We don't know what is this Hilbert space, but this is naturally part of the quantization. So we quantize in such a way. In the field theoretic version, you can, for example, look it up that the Poisson commutator, anti-commutators, or Poisson brackets are once again some not necessarily Kronecker delta, but Dirac delta, and we simply do the quantization procedure, and we arrive at these relations, and these relations will help us identify the Hilbert space of particles. So they are critically important. So remember that the quantization of the field follows this canonical quantization procedure, and this is supplemented by the assumption. So we promote the dynamical quantities to operators. We do the quantization procedure, and obviously, since we're promoting the operators to the quantities to operators, we have to assume that they act on some states in a Hilbert space. So this is how we arrive at quantum mechanics. Either no, this is not just like this canonical procedure is general. This is not just talking about field theory. This could be also used for, that is, to quantize the classical mechanics. So this is the Dirac's canonical quantization procedure. And let's find the, so let's first talk about, so if we do this, before we do that, we can also find, for example, the solutions of the Klein-Gordon equation. We do that by first transforming the Klein-Gordon, or taking the field and expanding it in the momentum, in formal momentum. And if we plug that into the Klein-Gordon equations, we get the Klein-Gordon equation in the momentum space. And we see why fields satisfying the equations of motions are called on mass shell, because they must, for any field, the condition p square is equal to m square must be satisfied. Therefore, these fields must be, or the components of these fields must satisfy individually, or the momenta must satisfy the fact that they are on, well, this is basically the relation. P square must be equal to m square. So the solution to these can be written simply as some function depending on p and the delta function that assures that this condition on mass shell condition is satisfied. And then we simply plug it into the formula for the position dependence of the field, and we get two components of in the field due to the Dirac delta function, where we've simply used the definition of when we're considering like a square inside the Dirac delta function. This turns out to be like sum of two Dirac delta function. We've defined what's known as invariant metric, and that was simply this one. And we've also used the fact that we have real scalar field, therefore the function depending on momentum can be written also as the Hermitian conjugate. Okay, so this is basically what we've arrived at. We have a scalar field that is somehow represented in terms of some function, and not necessarily a real scalar field. We can also consider this to be a complex scalar field. As we see, we didn't so far, well, we do assume that it is Hermitian at least. Okay, so this is the no, sorry. This is a real scalar field. Sorry, mistake. this this only holds for the real scalar field. But we see that uh, there are some complex variables like these a functions and plus functions. Obviously, like this is the Hermitian conjugate of the first one, so the resulting field is real. Sorry about the mistake. So now we need to find. Okay, so we got some expansion in terms of these two functions, momentum dependent. Now we need to find out what they are. We can simply do the inverse transformation. We can take the definition of or what we've arrived at, the formula for the field, and we can do an inverse transformation, and we will get that the coefficients are simply given in terms of the field itself. This is the energy, the EP, and the canonical momentum or the momentum field. And we can simply you we can simply uh, give them like this, or this is how they are prescribed. And now, with the use of the uh, canonical relations that we arrived at, thanks to the Dirac's canonical quantization procedure, these guys right over here, we can use them to calculate the canonical commutation relation between these two functions, because or operators, in fact, because then this will tell us something about what they are. So okay, so we can calculate it. We are literally just using these commutation relation, which give us delta functions or zeros, depending on what we are multiplying with. If we're multiplying the fields, then we will get zeros. If we're multiplying the pi's, then we will in the commutators we will get zeros. If we get the multiples of pi's and p's, then we will get delta functions. So there are two integrals. One will go away, and in the end, we will arrive at the following algebra that these operators must satisfy. And if, in fact, it is the algebra of creation and the annihilation operators as we know them from the treatment of linear harmonic oscillator. So in fact, these operators can be used as the rip or can be used in terms of the Fock representation. Therefore, that they indeed describe the creation and annihilation of operators acting on the Fock space. So we have identified these operators to be the operators acting on the Fock space, and therefore our Hilbert space is the Fock space. So if we postulate the existence of a vacuum, in such way that if we act with the annihilation operator that is zero, that the vacuum is normalized, then the many particle states are then simply given by states in the Fock space. So if we want to create a state where there are n particles, each one with a different momentum, then we simply act n times with the creation operator on the vacuum, and this is in the quantum mechanical sense the many particle state that is part of the Fock space. So now we have well-defined Hilbert space, and the operators are therefore representations acting on the Fock space. And once again, we have identified the one particle and many particle states. So this is the first ingredient. The second one will be very fast because we won't do it in detail. We need, of course, the representations of the Lorentz group acting on particle states, and this one simply follows from the transformation properties of studied fields. We don't have time to study how the fields themselves transform, so you can look this up. But we know that the annihilation and creation operators are defined in terms of the fields. Therefore, the transformation properties of these operators are defined in terms of the field transformations, and since the particle states are defined in terms of the annihilation creation operators, these are also defined in terms of the transformation properties of the field. So if we know the transformation properties of the field, we know the representations of the Lorentz group acting on the one particle state. So this is the 2 out of 3 ingredients. Additionally, since scalar field is, for example, rotation invariant, and if we acted on the one particle state with the third component of the angular momentum, which is usually the angular momentum associated with the axis along which it is quantized, then we would get that it is zero. Therefore, the state is annihilated by angular momentum, which means that the spin is equal to zero in the rest frame. So this tells us that our scalar field, the quantization of scalar field, is associated with spin zero particles in the which are the states in the Hilbert space, in the Fox Hilbert space. So we see how these properties of the fields are indeed related to the properties of the particles themselves. Once again, these particle states are the Fock states in the Fock space. Okay, so last thing, if these operators, which indeed shall are the only ingredients of the Lagrangian, therefore they can be the only ingredient of the physical observables, then are they operators acting on the Hilbert space causal? We need to check that once again from the definition that we gave a few slides back. We do the commutator, so we use the definition of the field or what we arrived at, and we simply do some calculations. Once again, so we use the commutation relations of the operators, and we get to the following final formula. And the first term, this is known as the retarded Green's function of the Klein-Gordon equation, and then from that we subtract also the retarded Green's function of the Klein-Gordon equation, except with the argument switched. And this difference is known as the Pauli-Jordan function. And this Green's function is, in fact, has some, it can be somehow evaluated in the position representation. But what is important is that the Green's function on its own, which is in fact, this retarded Green function is in fact what we've calculated the relativistic probability amplitude for a particle to travel between some points x and y. We see once again it is non-zero for space-like separated particles, but since it is even, this modified Bessel function of the first order is even, then since we're subtracting these two guys from each other, then the Pauli-Jordan commutator function, this gamma, then it is zero thanks to the evenness of this modified Bessel function. So we see that the operators are causal; they satisfy this causality condition. So we have 3 out of 3 ingredients, and therefore we have quantized the scalar field. Since we have we have done the quantization procedure, we have identified the Hilbert space. We have found representations of Lorentz group acting on this space, which are given, follow from the representation transformation properties of the field. This also reveals to us that these states are rotationally invariant, since the scalar fields are all rotationally invariant. So in the rest frame, the particles, therefore they are spin zero particles, and our fields are local and causal, and therefore can be used to construct observables. So we have 3 out of 3 ingredients from this canonical quantization procedure, and we have found that we have non-interacting, or we have constructed non-interacting quantum field theory of scalar or spinless particles. Non-interacting because we didn't consider any interactions or nonlinearities or additional fields or interaction between these fields. So obviously it is not very useful on its own, but it illustrates the concept of free particles, that they are some states in this Hilbert space, and that this state can be built up from the fields that we choose to quantize. And these are somehow the structure of these fields, whether they be scalar, Lorentz, they're a spinor, or whatever. This is related to the irreducible representations of the Lorentz transformations. So, okay, so once again, not a very useful example, but necessary example, because these free particle states will also serve as our initial and final states in, for example, in processes that we have described in the beginning. For example, the annihilation of electron and positron into 2 gamma photons necessarily takes the initial state as some free particle state of one particle, which is literally the one particle state that we have just shown of electron, and one particle state of positron. Then there is some interaction which we will describe, and in the final state we will have some 2 times excited vacuum belonging to the photons. So literally, this description of the Fock space and the arrival at it and the quantization of the field is what stands behind the machinery that we will employ in the next lecture, and you will see how this once again leads to Feynman diagrams in the and the rules associated rules in the next lecture. So okay, classical mechanics. This is what we've done. We first took the infinite. We've considered infinite number degrees of freedom limit, which basically is classical field theory, because we have infinite number of configuration coordinates. We could also arrive at quantum mechanics from classical mechanics by the procedure of classical or Dirac's quantization procedure and the supplementation of the Hilbert space on which these operators act. And that is how we could arrive to quantum mechanics. Then we could also, for example, in classical field theory, we could talk about relativistic classical field theory if we also constructed field theory that are relativist Lorentz invariant. This would, for example, lead to Maxwell equations. And then what we've done through the top-bottom approach is that we've quantized these fields. In the bottom-up approach, in fact, we would first construct the Hilbert space in the quantum mechanics from the knowledge of from the definition of the one particle states as the eigenstates of the form momentum. Then we would we would construct this infinite degree of freedom Hilbert many corresponding many particle states in the Fock, which would reveal to be Fock space as well. And both of these approaches lead to quantum field theory, which once again is when we have the associated the quantized operators, field operators, we have the associated Hilbert space, and in the case when we are also considering relativistic quantum field theory, we also know the representations of the Lorentz group acting on the Hilbert space and the locality and causality of our operators. So once again, we took this blue path over here, where we were first. This is the bottom-up description from the classical field theory. Of course, we were first describing but anyway, you can see that there are multiple ways, and you can see how these concepts somehow relate to each other. In both cases, quantum mechanics are retrieved from classical theory, from the classical or Dirac's quantization procedure. So this is the summary, and the next time we will discuss interactions and measured observables, measurable observables. We will do some comments on particles with spin, and we will dive into QED with Feynman diagrams and basically what they are, how to calculate them, how they relate to what we said in this lecture, and we will probably do some examples. The most important of which are, for example, the Compton scattering, the pair annihilation, the scattering of electron on some proton in some nucleus, for example. And we could consider also like Coulomb corrections, which are usually not discussed, and that show additional structure of atoms, for example. So it will be all rainbows from now on. This was the most, I guess, abstract of the three lectures, and then on we will simply start playing with Feynman diagrams and stuff like that. So once again, thank you for your attention, and I'll see you next time.